In the last video, we took a look at kinetic energy and its forms. We also looked at some different types of energy and its forms and looked at how things change forms. The other major type of energy that are going to look at is potential energy. We will look at some other forms as well, but the two main types that we're talking about are kinetic and potential. Potential energy is the energy that we have stored due to position. And this can actually be physical position, but it can also be due to the arrangement of the particles, like the difference in the arrangement of particles between a solid and a liquid. They have different potential energies. Other examples include things like an apple in a tree, as well as a stretched rubber band. Now, I know the slide here says three main types, but we actually have five that we're going to look at. The first one is elastic potential energy. This is the type of energy that is stored in objects that can stretch or compress, like a string, a spring, a ball even, a rubber band. Balls actually compress, and that's why they're actually able to bounce. Things that don't bounce can't compress. Now, this elastic potential energy is a unique feature of certain objects, and it's because of the arrangement of the charges within the atoms themselves. So that's why some substances are able to bounce and others aren't. The second type of potential energy is the chemical potential energy, and this is the one that we are probably most familiar with as humans, because this is the energy that is stored in bonds that holds atoms together. And we see this energy when we run chemical reactions in the lab, but also we get that from our food and in gasoline. The third type is electrical potential energy. This is the ability for us to move electrons because of the electromagnetic force. Basically, if you think of an electron, it is a negative charge, and when we create a positive charge, it actually pulls on those electrons, and that's actually how a wire works. You create this positive pulling force, and you pull the electrons through the wire to generate electricity. The fourth one we did talk about when we talked about the atom, and this is nuclear potential energy. Nuclear exists because all of our radioactive elements, which are elements 85 and above, have the potential to undergo fission, and all of our elements on the periodic table have the potential to undergo fusion. Now, I know when we talked about fusion, we really only talked about hydrogen and helium, and that's because that's what we're looking to use as humans for fusion. But really, all of the elements on the periodic table are capable of this. The last type of potential energy is the one that we're going to spend the most time with, and this is gravitational potential energy. This is the energy that is stored in objects based on their height above the Earth's surface. So as you move higher, the gravitational potential energy is going to increase. And for any object, the gravitational potential energy is always at its maximum when it is at the maximum height above the Earth. So if I have something sitting on the ground, it's at its lowest. It's going to be actually zero because its height is zero. But if I have something sitting up on a shelf, as long as it doesn't go higher, it's at its highest amount of potential energy. Gravitational potential energy represents the potential work that gravity should be able to do on an object. In addition to the height that we already discussed, it also depends on the mass. So things that have a greater mass are going to have more gravitational potential energy than something that is at the same height but a smaller mass. It also includes our acceleration due to gravity, which the value of that we know, which is 9.8 meters per second squared. Some examples of things that have gravitational potential energy include an apple in a tree or a diver in a diving board. So, because these are things that we can measure, we can actually do calculations with gravitational potential energy. The formula for gravitational potential energy is PE equals the m times g times h. So those x's are actually multiplication signs. Okay, m is your mass. G, just like in the last unit, is the acceleration due to gravity, which is 9.8 meters per second squared. H is the vertical height above the Earth. And again, because we are talking about energy, our unit is the joule. So let's take a look at some practice problems involving gravitational potential energy. The first one, a diver is standing on a diving board, and what is her gravitational potential energy with her mass being 50 kilograms? So we are going to write our formula first. PE equals mgh, and then I just simply plug in. Her mass is 50 kilograms. G we know the value of, which is 9.8, and h is the other number in the problem, which is 10 meters. When I multiply this out on my calculator, I get 4,900. Now I have to look at sig figs. Some of you may be saying, well, it's fine because 9.8 only has 2 sig figs. However, that is not a measurement, that is a constant. So we have to look at the actual measurements that we have, which are 50 and 10, and both of those have 3 sig figs in them. Looking at 4,900, it has only 2. Now usually our first trick is to put a decimal, but that makes it have 4, so I can't do that. The only option for writing this with 3 sig figs is to actually take it into scientific notation. So this is the first part of scientific notation. This is the exact same number because I jumped the decimal point 1, 2, 3, and because I have the 4.90, that part has 3 sig figs, and now my answer is finalized. Let's take a look at the second one. Alright, a 60 kilogram person walks from the ground to the roof of a 74.8 meter tall building. How much gravitational potential energy does she have at the top of the building? So her mass is 60 kilograms, G, still the same value, 9.8, and the height that she has moved is 74.8 meters. So when I multiply this out on my calculator, I get 43,982.4. And so now I have to look again at sig figs. Remembering that the 9.8 doesn't count, again I need to have 3. So I know I'm going to have numbers here. But when I have this 8, this actually rounds this up to 44,000. 44,000 only has 2 sig figs. So, if I put the decimal, it's just like the last problem. So again, my only option is scientific notation. 4.40 has 3 sig figs, and then times 10, and I have jumped the decimal point 1, 2, 3, 4 spaces, and my unit is joules. All right, number 3. We have a tennis ball, and it starts to fall from a height of 2.9 meters. How much gravitational potential energy does the ball have at that height? So PE equals mgh, and my potential energy is 0.06 times g, which is 9.8, and my height is 2.9 meters. When I plug this into my calculator, my answer is 1.7052. However, I can only have 1 sig fig because of the mass, so that rounds to 2, and my unit is joules. With the last practice problem, we again have a tennis ball, but it's a slightly different situation. Ball is being held outside of a second floor window that is 3.5 meters from the ground. And Betty is holding one outside a third floor window that is 6.25 meters from the ground. How much more gravitational potential energy does Betty's tennis ball have? So, if you think about this, we basically have, sorry, my pen went off again. There we go. We basically have a building, and on the first floor here we have Bob, and he's at 2.5, and then Betty is up here on the third floor and she's at 6.25. I'm sorry, Bob's at 3.5. So the difference in the potential energy has to do with the difference in the height between the two of them. So we can actually solve this problem in one step. Basically, the h here is going to be the subtraction between these two numbers. So the mass of the tennis ball is still the same, 0.06. G hasn't changed, it is 9.8. And now I subtract 6.25 minus 3.5. When I do that, remember you have to use the sig fig rules for addition and subtraction now. Okay, so I have 0.06 times 9.8, and the sig fig rules for addition and subtraction is least number of decimal places. So this actually becomes a 2.8, even though it comes up on your calculator as a 2.75. Now I multiply everything together, and my potential energy is 1.6464 on my calculator. Again, I can only use one sig fig, so this becomes 2, and the unit is joules, and I am done. Now the next video has a clip or an actual video that talks about both kinetic and potential energy, and then we will start looking at how we convert different energies.